Hallo und herzlich willkommen zu Industry.forward Expo. Mein Name ist Jessica Bischoff von Publish Industry und wir haben jetzt ein weiteres spannendes Thema hier. Ich habe auch zwei sehr spannende Speaker bei mir geladen. Einmal die Andrea Beuter, sie ist Senior Sales Managerin bei Real-Time Systems. Hallo Andrea. Und einmal den Walid Allaham, er ist Field Application Engineer auch bei Real-Time Systems. Hallo Walid. So, now we're switching into English. Andrea, Walid, the stage is yours.
So, hello everyone, good afternoon. My name is Walid Allaham. I'm the field application engineer at the company RTS in Germany. Please also allow me to welcome my colleague Andrea G. Beuter, our senior sales manager at RTS. Andrea, could you please introduce yourself?
Thank you, Walid. Hi, my name is Andrea J. Beuter, or shortly how most of the big people call me AJ. I'm a senior sales manager here at RTS, and together we plan, Walid and I plan for a ride through our technology for the next 20 minutes.
So,
Go ahead.
yeah, for organizational purposes, we will give the presentation. We are open for questions and discussion at the end. So please feel free to submit questions you have during the presentation via chat. So, who we are. Real-Time Systems company was founded in 2006 in Ravensburg, Germany, as a spin-off from KUKA Robotics. We are a part of Congatec company since 2018, but we operate totally independent. We are a market leader for hypervisor technology for the embedded market and experts in real-time virtualization. We're also an Intel co-development partner. Our customers are located in more than 25 countries around the world, and currently there are more than 100,000 hypervisor systems out there using our technology. Where we are located, our headquarters and development are located in the south of Germany, in Ravensburg, but we have offices and representatives in Europe, US, and Asia. You can find our technology used in different fields like industrial automation, robotics, medical, rail and test measurement, for example, like power grids, test equipment for the automotive market, as well as in other embedded systems, for example, in broadcasting and streaming. A typical use case in industrial automation would be that, for example, we have one hardware with multiple operating systems running on it. And in this case, as you can see in the screen, the general purpose operating system, in this case, it's the Windows, is responsible for, it's taking care of the HMI functionality. And we have also, in additional to the Windows, we have the Linux real-time operating system, which is split into several applications, like an application responsible to control the motors in an industrial machine, and another application responsible for controlling the robots, and an application for transferring the input and output data into the cloud, or even you can save the data. We know that in an industrial automation field, it is important to integrate computers and smart tools in order to perform multiple operations at the same time. And real-time is required in most of the applications. With our hypervisor solution, industrial factories can reduce numbers in hardware devices and cost, and gain performance and determinism, no delays when running real-time applications in a safe and secure way. In the following slides, we will explain more in detail how to overcome those challenges using our technology. So let's talk about the concept of the hypervisor. So what is a hypervisor in general? So for those of you who are not familiar with the hypervisor technology, I would like to explain the hypervisor concept to you shortly. So a hypervisor, also known as a virtual machine monitor or a VMM, is a software that creates and runs virtual machines. A hypervisor allows one host computer to support multiple guest virtual machines by virtually sharing its resources, such as memory and processors. A well-known concept in the IT world would be servers running in virtual machines, providing users with an environment where they can install, configure, and execute software without affecting other servers running on the same physical machine. Another typical use case would be where on a work workstation or laptop, users need to run a different operating system than the installed one. Running Linux inside Windows or vice versa is a common practice to work around operating system dependencies. In such scenarios, the virtual machine is typically far abstracted from the hardware and has little to do with the real-time machine. In today's world, you still have multiple servers performing different operating systems with its applications and peripherals, or shortly multiple controllers or PCs for multiple tasks are typically used. Let's dive into the hardware. We typically have in the industrial PC, processor cores, PCI devices, and memory. Today's computer, you have multiple cores. Different PCI devices are included on board or can be added as a plug-in device. The RTS Hypervisor splits the hardware into individual partitions. Each partition contains one or more processor core, some memory, and PCI devices. Different partitions may run different operating systems or multiple instances from the same operating system. In our solution, multiple hardware platforms can now be consolidated into one single PC, running different types of operating system. Real-time operating systems, which we call shortly RTOS, and general purpose operating system, which we call shortly GPOS, which can be Linux or Windows standard. Now let's move on to the different kinds of the hypervisors. So we have two types. A typical hypervisor from the IT world is not designed for real-time operation, and commonly known hypervisor types would be type 1, which is the bare metal hypervisor, and type 2 is the hosted hypervisor. So in type 1, which we are working with, the RTS hypervisor, bare metal hypervisor, guest operating systems run directly in virtual machines on top of the hypervisor, which has direct access to the hardware. It's a typical server configuration. In type 2 hypervisor, virtual machines run on top of a hypervisor running inside an operating system or in the kernel extension of an operating system, hardware managed by the operating system. This is often used in workstations and laptops. The RTS hypervisor allows real-time operating systems, or previously mentioned, shortly called RTOS, to access their portion of the hardware directly. Interrupts are routed directly to the correct processor cores and are processed immediately by the RTOS without interception by the RTS hypervisor. For processor cores running GPOS like Windows or standard Linux distributions, the RTS hypervisor sits in between the hardware and the operating system to ensure proper isolation. Now, to dive even deeper with our hypervisor, you have exclusive hardware assignment, which means you can assign processor cores with integrated timers and assign your PCI devices. Now, resource partitioning, you can also partition your resources like RAM and cache memory. Two different operating system execution modes that may run on different processor cores in parallel, what we call the privileged mode or the virtualized mode. With the privileged mode, we have direct hardware access, therefore no added latencies, and additional latency-free and hardware-assisted protection, which can be configurable with virtual MMU feature, restricted I/O, and I/O MMU feature. With the virtualized mode, you have pass-through access to assigned devices. You can run unmodified operating systems and update them at any time in terms of device sharing, for example, like mass storage disk partitions, AHCI or NVMe, USB ports, even behind USB hubs, XHCI. You have complete isolation of OS in memory. No interdependence. Reboot of any system is also possible at any time, and it's definable in the boot sequence. We also have more features for the temporal isolation. One of the first one is, for example, the time coordinated computing TCC, cache allocation technology, power management, GPU frequency, GT-Class, cache allocation technology, and memory access throttle MAT. In co-development with Intel, we can get access to pre-launch development ports and confidential Intel documentation. We have constant provision of additional functionality for increased real-time performance and are always supporting the latest chips through the early access program. Let's move from the concept into the features of our product. Andrea, would you like to continue from here, please?
Yeah, thank you, Walid, for introducing the concept. So to
Sure.
spin this even further, this is an overview of all the popular OSs we currently support. If you are further interested and would like to know our deeper, like the versions and everything, please feel free to reach out to us. So let's move into the different execution modes. Windows must run in virtualized mode, unmodified. Windows in general must not be modified. It's prohibited by Microsoft kernel patch protection and other new security mechanisms. Linux can either run in virtualized or privileged mode. In virtualized mode, standards isolations, for example, Debian, Ubuntu, we test with the latest long-term support versions, or shortly LTS. In privileged mode, we offer an RT or Xenomai kernel with Debian RAM disk, latest 2 LTS kernels included with the package. But we are also able to deliver older version, but standard is what I mentioned earlier. In the privileged mode, the integrated RTOS images remain compatible with future versions of the RTS hypervisor. Therefore, no need for BSP modifications when updating the hypervisor. And RTOS in general must run in privileged mode because it requires a real-time systems BSP, and we provide sample images built from our BSP. The final images are to be built and maintained by the customers. But no worries, if you need support for this, we can assess the work and see which services we can provide for you in order to assist you. Let's move a little deeper in the virtualized mode. For the virtualized mode, the RTS hypervisor runs installed GPOSes, as I said earlier, Windows or Linux, using the bootloader. We will explain the bootloader later on in more detail. The reboot of an OS running in virtualized mode does not affect other running operating systems, but assigned devices sometimes may require a hardware reset. As a difference to IT hypervisors, as Walid mentioned earlier, is the temporal isolation, meaning whatever has system-wide effects will be suppressed. You can update the OS, meaning you can install application and drivers in a running system. No virtual emulated PC run on OS as installed on the disk write, so using the same license. For RTS hypervisor, no virtual disk images are used. The OS installed on the disk drive runs on top of the RTS hypervisor. Users can choose between running a native OS as installed on the disk or running the OS within the RTS hypervisor, so in parallel to other operating systems. Instead of a virtual PC, the OS gets access to a portion of the real hardware, for example, CPUs, cores, graphics, or PCI devices. With the privileged mode, you can run multiple RTOSes using a BSP or board support package for those who don't know it. It is provided by us, but why do we have to use a BSP in the first place? First of all, it's an easy starting point. The BSP uses our Virtualization interface. Privileged mode allows for direct hardware access, but how you can tell the OS and what hardware is assigned. This could have been solved through virtualization, but this adds unpredictable latencies. The RTS BSP makes it transparent how to use resources, how they're allocated, and where to expect latencies. It makes the RTS hypervisor aware, for example. It tells the OS what resources might be used exclusively, what devices are shared. It provides inter-OS communication, and I will go later on in more detail about that. RTS API, for example, shared memory, event, or virtual network, which I will explain further on in more detail too. The PSP get provided free of charge for every RTOS we support. A generic BSP comes in source code. Customers use this as a starting point, for example, to match their BSP changes with ours. This enables build of an RTOS image to run on any x86 without modification. Sample images are provided for demo purposes or as a starting point. It gives you transparency on resource allocation, shared devices, and expected latencies. And it allows inter-OS communication. We can assign part of the memory to the GPOS and other parts to the RTOS. And if one of the OS tries to get access from the memory space not assigned to, the RTS hypervisor gets notified and virtualizes the access as if there was no addressable resource. A warning will be sent to the log, and of course, it needs time, latency. No latencies are added as long as the OS stays within its boundaries. Not just protection, virtual MMU and restricted I/O allow for emulated devices needed for device sharing. And all this is, of course, configurable. There are three ways of communication between the GPOS and the RPOS, and I will explain a little bit deeper. One is through shared memory. One or multiple shared memory areas can be configured. The size of the shared memory only limited by the amount of memory available by the system. Simple APIs provide access to shared memory from within each OS, provides lock mechanism read-write permissions, or through the virtual network using interprocessor interrupts. Network drives for each OS provide that reside directly on shared memory. Each processor core can have its own IP MAC address, regular protocols usable for communication like TCP/IP, OPC, or COBRA. Or it can be done through an event system. Users can wait in an OS for a named event, events signaled with the inter-processor interrupts, and that can be used for real-time applications. So we talked about communication, and now in order to take the OS talk to each other, we have special APIs in place, like OS control. It allows operating systems to shut down, boot, and reboot other operating systems. Should an OS no longer react, it can be halted or recessed. With a watchdog, every OS increases its watchdog counter periodically. We call it a heartbeat. Any OS can check the watchdog counter of any OS and react in a custom way. Or through time synchronization. So you define a master OS and have the other OS set the wall clock accordingly. Let's move along to device sharing. So if we follow the pass-through concept with exclusive assignment, a disk or USB controller will only be accessible by the OS to which the controller is assigned. In this case, to solve this, we allow for sharing certain devices. This is configurable. In this example, with a shared disk controller and a shared XHCI controller, only one disk partition is accessible for the GPOS and 2 out of 6 physical USB ports. Now, other OS may also get a disk partition and as USB ports assigned. From the OS point of view, it still looks like a normal disk, but with fewer partitions, and a normal XHCI controller with fewer USB ports. Now let's move on to the boot sequence. When you turn on the system, the firmware executes as usual, but then instead of a running OS directly, a bootloader starts. Users have different options here. For example, they can select a configuration with the RTS hypervisor or start the native OS, which is quite convenient for development. For example, The configuration contains an error and needs to be changed. Bootloader and ready-to-use configuration install automatically using provided installation scripts. This is what our default bootloader menu looks like. We typically use grep, which is a well-known to all of the Linux users here around. It's customizable. The bootloader can be hidden from the end user with default selection starting directly. So there's no user input required. But that's just one option. Custom, splash screens, boot selection may be added as required or desired. grep is a powerful and versatile bootloader, but can be replaced by any custom bootloader without the need for hypervisor modifications. For example, if you have additional requirements like secure boot, encryption, file signature verification, or decryption. So how does our configuration work? The configuration with the RTS hypervisor is performed through a simple text file. Every OS gets its own section in the configuration file and a unique number. In this example is OS 0, OS 1. It's easy and flexible, scalable configuration. Flexible in terms of the configurations can be applied to multiple hardware platforms, or you can cross-use it, however you want to name it. For example, we can assign devices only having the vendor and device ID. No detailed knowledge of the device resources are necessary. Scalable configurations can be used on low and high core count CPUs, regardless of the actual CPU topology. CPU cores or cache segments can be configured in percentages. We have multiple options for device assignment depending on use cases and application requirements. Different options can be mixed in the same configuration file. Of course, we also would like to highlight quickly what are the benefits of a real-time hypervisor. So in general, it reduces costs and required space, lower maintenance, less cables, less connectors, less spare parts, and of course, reduced power consumption. The secure design, it's secure OS separation with hardware partitioning. No unessential interfaces, no backdoors. Extensive rights management measures and secure boot. You get maximum performance, retain determinism of real-time applications, and rapid inter-system communication and synchronization. It increased productivity, less components, longer mean time between failure, simple configuration in plain text, shorter time to market, no hardware-specific adaptations are needed, intermediate use after installation, and efficient functional validation, simplified quality assurance and certification. It's flexible in the operation. Trouble-free charge of virtual machine combinations with open standards and interfaces. Easy manual changes without recompiling or retesting of other components. It's scalable, reusable, and upgradable. And last but not least, application optimized platform. One binary fits all. It's all popular OS are supported, all types and sizes of x86 Intel and AMD CPUs. And with that, I would like to thank you all for spending some time with us today. And I'll give it back to see if we have any questions dropping in.
Yes, thank you, AJ and Walid, for this interesting presentation. We've got plenty of questions. May I start with the first one? Can TSN technology also be used with the RTS hypervisor? What requirements must be met for this?
Walid, do you want to answer? Or
Yes, I think it can be used. The requirements are different from the application. But if if they would like to have more details, they can contact us and we can set up a meeting and we can talk about it.
Perfect. Yeah. To the viewers, if you scroll a little bit below, there is a pink button, email to the speaker. They can write AJ and Walid if you have further questions. But let's go on with this question. In industrial environments, real-time capability is a must today. Is this also possible with the RTS hypervisor, or are there technical limitations?
No, and we don't have any technical limitations. So as soon as it depends first on the application, and if we have the hardware, especially if it's coming from the x86 architecture, we can install the RTS hypervisor on it, and we can run multiple industrial automation applications with it without any problems.
Yeah, we can fulfill real hard-time bare metal requirements, but it also often depends on what we get delivered from the OSs, if it's a real-time operating system or another GPOS. We are even managing to increase the performance of a GPOS system. Yes.
Yep.
Thank you. The next question is, what are the minimum hardware requirements in terms of performance or power consumptions needed to use the RTS hypervisors?
Minimum requirements in terms of CPU power. This is a very, very broad question.
Okay, maybe also to the viewer, ask the question to both of them later on.
Yeah.
Maybe it's better to do it face to face. The next question is, how much does the product cost?
Well, that also depends on how many OSs do you want to consolidate on a platform. In general, it's very reasonable priced, so please feel free to reach out to us to elaborate your case, and we will come quickly and in a very unbureaucratic way with pricing.
Okay, maybe we do a last question. How does the communication between the two operating systems work?
Walid, do you want me to bring up the slide one more time?
Yes, please.
For that, hold on, let me see. But you can start talking. I will just try to get the slide up. I think it was slide.
So we mentioned three different ways of the communication between both operating systems. The first way is the virtual network. The second way is the shared memory. And the third way is the event system. Most of our customers are always using the virtual network, which is just an IP address assigned to the real-time operating system, and you can telnet from the native operating system GPOS to the real-time operating system, and you can transfer data and run applications on the real-time side. Yes, exactly. This is, you can see here on the slide how the intercommunication is working. So we have the shared memory, virtual network, and the event system. So with the shared memory, one or multiple shared memory areas can be configured. So in the configuration file, which is provided with the operating systems to the customer, you will find every operating system with a specific memory size from the shared memory. Depends, of course, it's limited because it depends on the memory available in the system. And a simple API provides access to shared memory from within each operating system and provides lock mechanism read and write permissions. In the virtual network, we're using inter-processor interrupts, network drivers for each operating system provided that reside directly on the shared memory. So if we have two virtual network Ethernet outputs on our hardware, we can assign each Ethernet controller to different operating systems. Like we can assign each one of the virtual networks to the first operating system and the second virtual network to the second operating system. Exactly. And each processor core can have own IP and MAC address, regular protocols usable for communication like TCP, IP, OPC, or CORPA. In the event system, user can wait in an operating system for a named event, just like an interrupt event, events signaled with inter-processor interrupts and can be used for real-time applications. Yeah.
Thank you, Walid.
Thank you. yeah,
You're welcome.
actually running out of time. If you've got further questions to AJ or Walid, don't hesitate to contact them. You see the email address below, as I've already mentioned. Thank you, you two.
Thank you so much.
Thank you.
And yeah, I think I'm switching again into German. Danke auch fürs Zuschauen und Zuhören und bis zum nächsten Mal.